Hello everyone, welcome to this lecture series on thermodynamics. Today in this series, let's discuss entropy. So, we have already studied in order to know the state of a system, we require the fundamental physical quantities, temperature, pressure, volume, internal energy. Like these physical parameters which are used to describe the state of a system, entropy is also the physical quantity which is used to describe the state of the system. This concept of entropy was first introduced and coined by a German physicist, Rudolf Clausius, in the year 1850. It is nothing but the thermal property of the body which remains constant during an adiabatic process, just as temperature remains constant in an isothermal process. It is generally denoted by S. So what is entropy? Entropy is the physical property which remains constant in an adiabatic process. We know that temperature is the physical quantity which is remaining constant in an isothermal process. Entropy is also defined as the measure of randomness or disorderness of the system. Now, we will see the concept of entropy. This provides deep insight into the direction of spontaneous change for many everyday phenomena. This entropy is having wide range of applications in the field of physics and chemistry, biological systems and their relations to life, cosmology, weather science, climate change and information systems, and transmission of information in technology and telecommunication. Now let's explain this concept of entropy. In order to understand this entropy, let us consider the three isothermals at temperatures T1, T2 and T3 and the two adiabatics A and B. Now from the figure it is clear that these two adiabatics A and B cut the isothermals at AB, CD and EF. AB, CD and EF. That is the first isothermal at AB, second isothermal at CD and third isothermal at EF. Now from this figure we can identify two Carnot cycles. ABCD is one Carnot cycle, DCEF is another Carnot cycle. Now let's consider the first Carnot cycle ABCD. ABCD. Let Q1 be the amount of heat absorbed by the working substance from the source which is at a temperature T1 and Q2 be the quantity of heat rejected to the sink which is at a temperature T2. Then for this engine working between this cycle of operation, we can calculate the efficiency as eta is equal to 1 minus Q2 by Q1, that is 1 minus T2 by T1. On simplifying, we will get Q1 by Q2 is equal to T1 by T2. Now let's consider the next Carnot cycle DCEF. Here the Q2 is the quantity of heat absorbed and Q3 is the quantity of heat rejected. Then also we can calculate the efficiency, and on simplifying we can write Q2 by T2 is equal to Q3 by T3. Now making use of these two equations, equation 1 and equation 2, we can write Q1 by T1 is equal to Q2 by T2, that is equal to Q3 by T3, which is a constant term. Q by T, ratio of quantity of heat absorbed to the temperature. This is remaining constant. Q by T is the parameter which is remaining constant. That means when a system changes from one adiabatic to another adiabatic, then either heat is absorbed or rejected. The amount of heat absorbed or rejected depends on the temperature. Suppose if Q is the quantity of heat absorbed or rejected by a system at a temperature T, when a system changes from one adiabatic to another adiabatic, then as we have already seen, that the ratio of quantity of heat absorbed or rejected to the temperature is the term which is remaining constant. So this is the ratio which is remaining constant. So this constant ratio is known as the change of entropy of the system when it changes from one adiabatic to another adiabatic. We have already understood that in an isothermal process, temperature remains constant. So what is entropy? Entropy is that which is remaining a constant during an adiabatic process. So this is one adiabatic process, this is one adiabatic process. When a system is changing from one adiabatic to another adiabatic process, it is either absorbing a quantity of heat or rejecting a quantity of heat, and this ratio is remaining constant. So Q by T is the quantity which is remaining constant. Now, if S1 and S2 be the entropies of the system at the adiabatics A and B, then we can write the change in entropy as S2 minus S1 is equal to Q by T. So, if two adiabatics are very close to each other and dQ is the quantity of heat absorbed at temperature T in changing from one adiabatic to another adiabatic, then we can say that the small change in entropy is given by ds is equal to dQ by T. That means heat absorbed or rejected by the absolute temperature. So Q by T is the quantity which is remaining constant during an adiabatic process. Now let's see the physical significance of entropy. So entropy is the physical parameter which remains constant during an adiabatic process. It is a definite function of the state of the body like temperature, pressure, volume and internal energy. Now, according to the definition of entropy, the change in entropy is equal to Q by T. That means heat energy by temperature. From this equation, heat energy is equal to change in entropy into temperature. From the above equation, we say that the heat energy has the same dimensions as the product of entropy and absolute temperature. According to classical mechanics, we know that potential energy is equal to mgh. mgh, mass, m is the mass, g is the acceleration due to gravity, and h represents the height. If we compare these two equations, equation 1 and equation 2, the entropy corresponds to mass or inertia, and we may take temperature equivalent to height, heat energy to potential energy, then the change in entropy corresponds to mass or inertia. Hence, we may think of entropy as the thermal inertia in heat motion, which is similar to the mass in linear motion or moment of inertia in rotatory motion. So, this is the physical significance of entropy. So, it is clear here, heat energy is equal to change in entropy into temperature. Potential energy is equal to m into h, where g is the acceleration due to gravity. If potential energy is compared to heat energy and height is compared to temperature, then the change in entropy can be taken as mass. Next, coming to the properties of entropy. So, entropy is a thermodynamic function. We can say it to be as a state function. It depends on the state of the system, but it does not depend on the path which it has followed. It is represented by S, and the units in SI system are joules per mole, and in CGS system calories per mole. So entropy is an extensive property, which means that it scales with size or extent of the system. Now let's try to calculate the change in entropy, that is measurement of entropy changes. The change in entropy in the case of a reversible process and the change of entropy in the case of irreversible process. Now let's calculate the change of entropy in reversible process. The measurement of entropy of a system when it is in one state is not possible. That is, we cannot calculate the entropy directly. We can only calculate the change in entropy when it changes from one state to another state. We have already understood the change in entropy is nothing but dQ by T. Now, let's consider the Carnot cycle ABCD, which represents a complete reversible process. During an isothermal expansion AB, the working substance absorbs a quantity of heat Q1 at a temperature T1. Then the change in entropy S2 minus S1, or the increase in entropy, can be written as Q1 by T1. During adiabatic expansion, B.Sc, the working substance does not absorb or reject heat. Hence, there is no change in entropy. Therefore, during an isothermal compression CD, the working substance rejects a quantity of heat Q2 to the temperature T2. Therefore, the decrease in entropy is Q2 by T2. Again, during the adiabatic compression DA, there is no change in entropy of the working substance. Therefore, so here there is increase in entropy, here there is decrease in entropy, here the entropy is remaining constant, here the entropy is remaining constant. So the total change in entropy of the working substance during the reversible process can be taken as the change in isothermal expansion and change in isothermal compression process. Hence, Q1 by T1 minus Q2 by T2. But from the definition of Kelvin scale of temperature, we know that Q1 by T1 is equal to Q2 by T2. So change in entropy is 0. Hence, we can say that the total change in entropy during a reversible process is 0. So measurement of entropy changes. We have calculated the total change of entropy during a reversible process by taking the Carnot cycle. So the change of entropy during a reversible process is 0. Now let's calculate the change of entropy in irreversible process. What is the best example for irreversible process? The transfer of heat between the two bodies can be taken as the best example for irreversible process. Of course, the transfer of heat by conduction and radiation are also examples of irreversible processes, and all the processes which are available in nature are irreversible process. Now let us consider a system having a hot body at a temperature T1 and a cold body at a temperature T2. Here, a quantity of heat Q flows from hot body to cold body according to first law of thermodynamics, or according to second law of thermodynamics, heat always flows from a body of high temperature to a body of low temperature. Now, let Q be the amount of heat transferred from hot body to cold body. Then what happens? Decrease in entropy of hot body will be Q by T1, while the increase in entropy of the cold body will be equal to Q by T2. So the total increase in entropy of the system is Q by T2 minus Q by T1. This is nothing but positive. That is, the entropy of a system always increases in an irreversible process. Since all the processes in nature are irreversible, the entropy of universe always increases. So we have calculated the change of entropy in an irreversible process, and we have seen that the entropy always increases. Now let's discuss the concept of entropy and disorder. So we have already seen that entropy is a measure of disorderness of the system. According to Boltzmann, we have seen entropy is a measure of disorderness, or we can call it as the randomness in the system. It is very clear that if a system absorbs heat, then the entropy of the system increases and disorderness of the molecules also increases. For example, let us consider the three states of matter: solid state, liquid state, and gaseous state. We know that in this case of solids, all the molecules are aligned, whereas in the case of liquids, there is somewhat disorderness, and in the case of gases, the disorderness increases. The molecules are free to move. So when a solid is converted from solid to liquid, when it is converted into liquid and then to vapor, what happens? The entropy increases. So what is happening here? The randomness is increasing. That means disorderness is increasing. That means entropy increases. Similarly, when the system rejects heat, entropy and disorderness of molecules decreases. That is, when a gas is cooled, it becomes into a liquid, and on further cooling, it becomes a solid. That means the entropy decreases. In general, entropy increases with increase of temperature. Moreover, according to third law of thermodynamics, at absolute zero temperature, crystalline structures are approximated to have perfect order and zero entropy. Now let's see entropy and the relation of second law of thermodynamics. So what is second law of thermodynamics? It gives us the direction of any physical or chemical process in which the change in energy takes place. So we know that entropy remains constant in a reversible process while it increases in an irreversible process. Thus, in any natural process, entropy of a thermal system either increases or remains constant, but it never decreases. Therefore, the second law of thermodynamics can be expressed in terms of entropy as every physical or chemical process in nature takes place in such a way that the total entropy of the system plus surroundings increases. Total entropy is nothing but total entropy of the surroundings and the system, which always increases. Now, let's discuss the concept of entropy and unavailable energy. So, the second law of thermodynamics tells us that whole amount of internal energy of any substance is not convertible into useful work. Only a small portion of the energy is used for doing useful work, which is called as the available energy, while the remaining part of energy which cannot be converted into useful work is called as unavailable energy. So entropy is a measure of this unavailable energy. In fact, entropy may be regarded as unavailable energy per unit temperature. So entropy is equal to unavailable energy by temperature. From this, unavailable energy is equal to entropy into temperature. Or the concept of entropy is of great value and it provides the information regarding structural changes accompanying a given process. Hope you understood the concept of entropy. Thank you.